power transformer connection. So power transformer can be connected in the star delta star. So this connection is a YY0 connection. YY0 means the primary connection connected in the star. Secondary connection, the secondary winding also connected in the star. So in this case, our primary vector voltage winding, so the A2, B2, C2, and secondary voltage winding, small A2, B2, C2, they are parallel. So therefore, the phase difference is 0. So this is the we can write down as this connection. This is the YY0. So this is the typical connection this way. And so this is the group 1, connection 1, primary star, secondary star. 0 means that this is a no phase difference between the primary and secondary voltage vector. So this is the YY0 connection. So based on this YY0 connection, we can also make the other separate connection. Group 1 connection 1 is a YY0, DD0, and DZ0. So in this case, phase difference is 0 connection, 0 degree. Group 2 is as a YY6, DD6, and the DZ6. Phase difference is 180. So this means the primary voltage and secondary voltage are 180 degrees different. Group 3 is a DY1, YD1, and the YZ1. Primary delta, secondary 1, secondary star. So this is for the 1 o'clock position. In this case, phase difference is minus 30 degrees. Group 4 is a DY11, YD11, and the YZ11. So phase difference is plus 30 degrees. So those are the kind of the transformer connection. So those transformer connection, this is just a phase angle, typical vector diagram, and connection delay diagram are represented in the transformer connection chart. So you have to study the transformer connection chart. So you will see the all kind of the connection, YY0, YY6, DD0, DZ6, and those kind of the delay connection and the respective vector diagram. Okay, now that we draw the typical HML connection, we have to connect the DY11 connection. DY11 connection, this is the primary windings are the capital A1, A2, capital B1, B2, capital C1, C2. And secondary winding is a small A1, A2, small B1, B2, and small C1, C2. So this is 3-phase winding. So primary 3-phase, secondary 3-phase. We want to connect the DY11. So firstly, we see the DY11 connection. We follow the transformer connection chart. So in the transformer connection chart, the DY11 is this connection, this diagram. So we have to apply this diagram. So in this case, you see the primary sides as capital A1 and the capital B2s are connected. So capital A1 and the capital B2 connected. And also the capital B1 and C2 connected. B1, C2 connected. Capital C1 and the A2 connected. So that this is C1, A2 connected. So then A2, B2, C2 connected to the supply. A2, B2, C2 connected to the supply. So this is for the primary, the D. The secondary is a Y11 connection. So the A1, B1, C1, small A1, B1, C1 are combined and connected to the neutral. Small A1, B1, C1 connected, combined and connected to neutral. And small A2, B2, C2 connected to supply. A2, B2, C2 and connected to supply. So this is the DY11 connection. So these DY11 connections are in the transformer connection chart. It show the DY11 must be connected this way. So we follow this diagram and then we connect. So this diagram will be the DY11 connection. So then, why we make the transformer in a different connection? The reason is YY0 and YY6 connections are suitable for the small high voltage transformer and the 3-phase co-die transformer. DD0 and DD6 are suitable for large low voltage transformer. So then, it is a distribution side. The high voltage is stepped down to the low voltage. In this case, those are low voltage distribution transformers are connected in DD0 and DD6. DY and YD. So this is the primary delta, secondary star, primary star, secondary delta. Those transformers are the suitable for the power supply transformer. And the transmission side, primary side connected in star, secondary connected delta. So 3-phase line is a 3-phase line without neutral are transmitted. And when they close to the distribution center, so we use a DY transformer, primary delta, secondary star. So the 3-phase 4-wire can be supplied from this transmission distribution transformer. So the power supply transformer, we can use a DY and YD transformer. And YZ and ZY, so primary star, secondary ZZY name, secondary primary ZZ, secondary star Y name. Those transformers are suitable for the earthing transformer. So by making the YZ connection, that harmonic can be reduced. So that harmonic reduction, we have to use the YZ and ZY for the admin transformer. Okay, so we will solve the problem for a 3-phase transformer equivalent circuit. So this problem given as a 10 MVA, star connection, primary voltage 33 kilovolt, secondary 11 kilovolt. When we are making a no-load test, so line voltage is 11 kilovolt, line current is 15 ampere, power 75 kilowatt. We made a short circuit test, line voltage is 1650 volt, line to line current is a rated current, and power is 90 kilowatt. So firstly, we do the no-load test. No-load test means that we supply the voltage at the low voltage side, high voltage side is open. So that here low voltage side is secondary. All value we use we get that are secondary value. So this is for the low voltage side. Okay, so no-load test we can calculate. So in this case RO. So RO is EO is equal to, so voltage is 11 kV. So this is the line to line voltage star connection, so divided by root 3, so 65 kilovolt. And also there's power. This power is given as 75 kilowatt. So this is 3-phase power, so divided by 3, so 25 kilowatt we got 25000. So this is for the R0. R0 means transformer co-resistance. The formula is V0 squared divided by V0, 6050 squared divided by 35,000. So you got the 16130. And also there's a current flow into this transformer core. This is the V0 by R0. 6050 divided by 16130, so 3/94. So the current flow to the magnetizing component is the formula is square root of I0 square minus IR0. So the I0 is a 15 ampere square, and the IR0 is a 3.94. So you got the 40/47. So the magnetizing component is V0 by IA0. So V0 is 65. And IA0 is at 40/47, so 438.8. So the two values are that we get at the secondary side. So that we refer to primary, we have to multiply tan ratio square multiply resistance. So tan ratio is a primary voltage 1133, secondary voltage 11, so 33/11 square multiply 161, so 14/5 kilo ohm. And similarly A0 dash, tan ratio square divided by secondary side inductive reactance, so 33/11 square multiply the 438.8, so the 3.95 kilo ohm. So the transformer co-resistance and co-inductive reactance can be calculated by this way. And then we will do the short circuit test. Short circuit test is a voltage is given the 1650. So this is the line to line voltage divided by 23, so 953 volt. And the power 90 kilowatt, so 90 divided by 10 power 3 divided by 3, so you got the 30s are down there. And also the current is a rated current. Rated current in the transformer MVA here, rated voltage this one. When you're making a short circuit test, low voltage side, lower voltage side have to be short circuit, or reading have to be taken at the high voltage side. So all reading we got are the primary voltage side, because primary is the high voltage, secondary low voltage. So the rated current can be calculated. So power is at 10 MVA, 10 into 10 power 6, root 3, and voltage is at 33 kilovolt, 33 into 10 power 3. So you got a 175 ampere. So the equivalent resistance is a short circuit power divided by equivalent current square. So short circuit power is already given here. So this is for the 30 kilowatt. So 30 into 10 power 3 divided by current square, 175 square, so 0.98 ohm. Equivalent impedance, short circuit voltage divided by short circuit current. So short circuit voltage is at 953, short circuit current is at 175. You got the 5/4 ohm. So we can also calculate the equivalence of inductance. Square root of Z equivalent square minus R equivalent square. So Z equivalent is we already calculated. So 5/4 square, R equivalent is 0.98 square. So square root, so you will have 5/3 ohm. Then we can draw that equivalent circuit diagram. So this is 0.98 and 5/3, equivalent resistance, equivalent inductive reactance. 14.55 kilo ohm co-resistance and 3.95 kilo ohm co-inductive reactance. So by this way we can draw that 3-phase transformer equivalent circuit. We take the 3-phase transformer, apply the single phase equivalent, and then we find RO, SO, REQ, ZEQ, and then you can draw the diagram.